Okay, so in the last unit we saw that the sign of the derivative in an interval determines whether a function is increasing or decreasing, right, at some point. And if it's equal to 0, then the function will have an extrema or an inflection point at that point, right? Now, using Taylor's theorem, we can, with the remainder actually, we can use that information of the higher derivatives to say more about the local behavior of a function around the point. Okay? But first, before going into that, we need to define some of these behaviors, how to characterize that behavior around the point, right? And so this is the important property of characteristic of convexity, right? So we say that a function f is convex at x equals a if it is locally above its tangent at that point, okay? And that algebraically this means that f at x is greater than f at a plus f prime at a times x minus a for all or those values that are close to a, right, between epsilon and minus epsilon for some epsilon. Okay, so that's what this means, right? The function is this blue line, and the red dashed line is the tangent at that point a, right? This is a, right? So here the function is above it, right? Because the values of a function are greater than the values of the tangent, right? Now, if a function is below the tangent, we call it concave. And if it's neither above or not below, which means that, you know, the sign changes, the sign of x, f of x minus f of a minus the f prime times x minus a changes between when x is smaller than a and x is greater than a, then we say that f has an inflection point at a. Okay, so now how can we characterize these things with Taylor expansion? Okay, so again, we suppose that f is infinitely many differentiable, and that we have zero derivatives, okay? Zero derivatives between f prime at a and some nth derivative f n divided by f, okay, at a, right? So this is the first derivative beyond the first that's going to be different than 0, okay? We say it like that because, well, many times it will be the second derivative, right? But if it's not, then the theory that we will develop now, it's valid for higher derivatives, right? So now we can express f using Taylor's theorem. So this is f is going to be f at a plus f prime at a times x minus a, and then all the derivatives are going to be 0 except the nth derivative. So we can express this using the remainder, the Lagrange remainder, divided by f prime and then times x minus a to the n, right? And then again, c is some value between a and x, right? So if it's important to stress that, you know, we know that this derivative is different than 0, right? If c is sufficiently close to a, this derivative will also be different than 0 and will have the same sign. Okay, that's this one. Okay, so we don't really need to know this one, but we can, the arguments that we're going to make will depend on the sign of this derivative, and we're going to assume this has the same sign as this derivative. Okay, the nth derivative at a. Okay, and this is going to be true as long as we're sufficiently close to c. Okay, now we can rearrange this as, let me write this directly like this, as f minus f at a minus f prime equals this, right? So the convexity of the function will be defined by this sign, right? So if this is, let's call this a function, you know, c of x, right? So if c is greater than 0, then the function is convex in A. If it's smaller than 0, then it's concave, convex, concave. And if it's neither, smaller than 0 on the left, well, if change sign, let's say it changes sign at A, then that means that there's an inflection point. Okay. Okay. So then this function c, as you can see, the sign will depend on the sign of the derivative, and also on this, depending on the power of n, right? So let's see, if n is odd, right, then the sign of f, the nth derivative of n of f will that don't matter, because this product will change sign at both sides of a. Okay, so when x is smaller than a, this will be negative, and so this will be negative when raised to the power n. But when x is greater than a, this will be positive, right? So we have different sign if n is odd. So if the first derivative that's different than 0 at a after the first is odd, then automatically we have an inflection point. Okay. Now if n is even, then we can have we know that x minus a is positive. So now the difference depends on the sign of the derivative. So if the nth derivative at a is greater than 0, then the function is convex at a. If the nth derivative is smaller than 0, then it's concave. And then that's it. Yeah. So let's see. If we also have that the derivative is 0, right, which means that the tangent is flat, then it doesn't change for n, odd n, it doesn't change, it's still an inflection point, but this is going to change. But for n even, right, then the point is going to be an extremum, right? That's what we know. So it's going to be a convex extremum or a concave extremum. So convex extremum is maximum, minimum. A concave extremum is a maximum, right? So in other words, this is a classical, the extension of, in most application, n even is going to be 2. So if the second derivative of f at a is positive, then this function is convex, and what we have at a is maximum. And if the second derivative of f at a is negative and f prime is 0, we have a maximum. Okay, we can summarize everything here in this table, right? So if n is odd, then it doesn't matter what sign the nth derivative is going to have, we always have an inflection point, right? N is the first derivative of f that's different than 0 after the first one. Okay. Now if n is even, it depends on the sorry, this is wrong, this is concave. Okay, this is an erratum. So if n is even and the sign of the derivative is positive, the nth derivative is positive, in many cases it will be the second derivative, right? The second derivative or the nth derivative is positive, then the function is convex. But if the derivative is 0, then it's not only convex, it's a minimum, right? And then if n is even and the sign of the nth derivative is negative, then the function is concave. But if the first derivative is 0, then we have a local maximum.